So we're going to be dealing with like lists and patterns today because we're making a finger jointed geometry. And what? It works? Excellent. So we just have to assume that what we did last week is what will be being brought into what we have this week, which might be a little bit different. So I'm just going to help you guys create like a set of components that will convert what you did this week, what we're doing with this file this week, to look like it was last week. So then we can then reconvert it back to this week again. Does that make sense? Like, imagine I wanted to teach you guys how to translate something from, let's say, Japanese or Chinese to English, but the sentence that we had was in English. First, we have to convert it to Chinese before we can then try and then convert it back. Yeah? So that's kind of what we have to do. So does this kind of look familiar? Anyone? No? Doesn't look familiar?
No.
Doesn't look familiar at all? This form? Okay, so what we have to do is it's probably best that we work with this particular starting script, but the idea is that this information here can be the work that you did last week. And so all the parametric elements that we scripted last week can feed into this. Okay, we are recording, we are good to go. So if we just quickly open this file up and select the elements, you'll note that it's slightly different to how we worked. Remember, we had these elements that were almost like pyramids. We had like a curve on the outside and a point in the middle, and we created weird 3D pyramid that goes to that point. Christina's group didn't do that. They did it a different way. It's actually probably a slower way when it comes to coding. But what it does mean is that the outcome is that you get 4 separate lists with 4 different objects. For example, if we call this top left, top right, bottom left, bottom right, you get lists of bottom right, bottom left, top right, and top left. Okay? So before we sort of move on to the whole process, is everyone using this script? Just to double check. So just to show you how to get if we assume that we're working with our old script, all we have to do is grab this component called graphed, and I'm going to put on bifocals. So we want graph tree. So we want to graft each of these. We're then going to grab the component merge, which you can find here. Yep. Yeah, this should work. then we are going to grab brep join. Now, guys, I'm just effectively just doing this step by step and not really explaining what this stuff does, just because we're just setting this up to get this right. Everyone's doing this at the same time. And then if we then get the component flatten, brep join, you can find that under surface in utility. I'm going to do this. Is that better? Yeah. Is that better for you? Okay. And so we should all have something that looks a lot like this. What this is doing is effectively turning, pardon? You don't have a list? Is that, you just don't have a panel? Okay, so what you'll note is if you grab a merge, and as you drag components into it, see how it automatically adds a third one and then a fourth one?
We have to join this too. Yeah.
You've got to plug into it.
No list coming up. I had the wrong one.
Yeah, grab a panel, which is a yellow squiggle, and then plug the flatten into the panel.
Flatten into the panel?
Yep.
That way?
Yep.
Cool. Cheers.
You can get this script off Moodle.
You know last week, you know how we drew from grasshopper to that?
From Rhino?
Yeah.
Yeah.
But this one, how is drawing just on the rhino and then we translate it to grasshopper?
So those surfaces have been embedded into the grasshopper file. Okay, don't worry. It's this. We're just doing this for ease of access. But imagine last week we got to a certain point and then we go to be continued, right, in that file. And then this file is just sort of like a continuation from last week. And Christina and I, we've embedded these surfaces in so that we don't have to necessarily worry too much, whether we've made something too thin or too wide. We can just focus on this geometry and the process that it gets applied to it for this week. So now what this has done is it's joined each of these surfaces back into what you would have got prior to extruding the geometry from last week. So do you remember at this point, this would have effectively looked like this, extrude point, and then we plug that into an extrude. So it's this component here, the extrude point, that we would then keep moving, and now we're going to break this up so that we can do a finger jointing. So I see a lot of people doing laser cutting, and they have a very powerful machine in front of them, and they have very powerful software at their fingertips, and they don't actually use either tools to the full capacity that they could be used at. So those of you does anyone here literally just laser cut rectangles sometimes? Like that's a wall, right? And you just laser cut that, right? So the laser cutter is an incredibly accurate machine that can do really fine details. At the same time, it can do large, broad cuts, right? So there's always like this factor of, okay, if I were to take this element and I want to join it onto an element, let's think in 3D now, like so, what could we do with the materials that we're cutting so that when those two pieces come together, they're perfect, right? They come together perfectly. Yeah, we could quite easily score a gap, like so you know where to put it, but you could actually laser cut little notches on the edge of your material, and this one here, if you were to look at that in elevation, would then have two little holes in it so that those two things plug together. Can you hear? Okay. He's just pointing at your ears like, "Rrr, my ears." Okay, so the fact of just adding that tiny little bit of detail to the edge of it can mean that you can put the materials together faster, more accurately, and it would actually be stronger, okay? So this is where finger jointing comes into play. It's a technique that's come out of woodworking from a long time ago. We can see a lot of Japanese woodworking techniques use this idea of finger jointing, and modern day woodworking has made it much easier with routers and laser cutters. And I've lost my cloth somehow. Okay. So, remember last week how we did a pseudocode? This week we're going to do another one, okay? 2 brain cell mans coming back out, and we're going to do a pseudocode. So, if I were to just draw a box in plan with its materials, like with thickness, right? And we consider that each of these edges is like a piece of timber, and I lay them out flat. And this box is 10 by 10 by 10 by 10, and the material thickness is 3. How long does this piece of timber need to be? Just pick a number. Pick something that seems sensible. Huh? 13? So if it was 13, it would be 3 mil longer than what the box is. So let's go with 10, right? Okay, so this is 10 long. Then I draw the next piece, this one. How long is that piece going to be? Right. This piece? 10? And this piece? So they're going to clash, right?
No, the one has to be short.
One has to be shorter, right?
Or you can make it like
Mitered, but let's say we can't miter it, right? There's no miters. We can't do a miter. We can only have a vertical cut. How long does the first piece need to be? 10 and then 7, and then what's the third piece? 10? Okay, so another way that we could do it, it's not 7 actually. What is it? 10 minus 3? 4, right? Okay, so we can, what if we want to make all the sides the same length? What would they have to be? I'll draw it bigger. So we have one piece that goes like so. Then another piece that goes like so, then another piece. Yeah? They're all the same length now, right? How long are they? Right, okay. So now we can all recognize that the pieces would clash at the corners, yeah? So, you know, if you make them all the same length, they clash at the corners. If I did finger jointing, right, meaning if I had a pattern like so, and a pattern like, I'm going to try and draw this so that I don't give away the answer. Right? So, in that corner, they can exist. There's either one existing or the other existing, right? Like, as a finger joint. How long would they need to be? From this point to this point, like including the finger joint. Who said 7? Who said 10? Correct, okay? Because it's going the full length, right? Okay, so we got that? So I'm just leaning you guys into thinking about finger joints. Okay, so now, that means both sides of the material have finger joints, yeah? Please instruct me to now do a finger joint. Remember how you gave me instructions last week on how to draw the thing? What's step 1? Have a go at what is step 1? There's no surfaces here for 1. We've got curves. So what am I doing? Which curve? Right, okay, so we need to somehow separate the edges to just get the 2 vertical ones. Okay, we've done that, right? So we've got 2 vertical edges. Yeah? Now what? I love hand gestures, but words are better. Divide. Okay, so last week we did a divide. Did we? Yeah, we did. Last week we did a divide. What did we end up when we divided? We took a curve and we divide it. What do you get? Right. You get points. Is there a different outcome that you'd be looking for? Can you divide a curve and get something else? Like, pardon? You get a subcurve, yeah? So you can divide curves and get subcurves, yeah? Okay, so let's say that's what we want, yeah? So from now on, let's use the term shatter. So when we want to divide a curve and to get curves as an outcome, shatter. So what do we want to do? And how do we want to shatter? Just give me anything, like think. Like if I shatter this curve, I can just shatter it there, right? Do we want to shatter evenly? Yeah. With the distribution? Okay, so we'll shatter evenly. And we're going to do that to both. Okay, what next?
You need to shift the shatter from the other side.
What does that mean?
I don't know, so you've got your points that you shattered.
The subcurves?
Subcurves. You want them to move down.
Why?
Because otherwise they won't fit each other.
Okay, just remember, so let's say this is 10.
Yeah.
No. That's 7. Yeah? So when you say move them down, what do you mean?
So say you've got making your finger joint like that. So you've got that one sticking out, that one sticking out, that one sticking out.
Yep, just like
so
fingers.
You want to move your
Just like fingers.
Yeah.
Yeah.
You want to move it down so you can make this one go in.
Right, okay, I like it. Okay, keep that thought in mind. It's really good, okay? It's the right thing to think. I'm just going to lead these guys down a path, okay? You're thinking the right thing. What do I do? What do I do to these lines? Exactly, right? So we want to do something to only half of them, yeah? So, you know, we only want the odd ones to be affected. Because if we did something to all of them, then we wouldn't end up with a finger joint. Is that kind of what you were thinking?
That's what I was trying to say. Yeah.
Right, okay. So for example, let's do something to only the even ones. Okay, what am I going to do to the even ones? Were you in my class last week?
I was in that class.
Okay.
Extrude it out.
Extrude? Okay. Let's use another word. Just, what do you want? Move?
Yeah.
Move? Okay, what am I doing? Move all the even ones outwards. Okay. Like so. Yeah? Now, I'm being really specific with the words that you're using, okay? You said outwards. Yeah? If you had said left, that would have been better. If you had said, but it still wouldn't have worked for all situations, okay? So if I move these outwards, then if I take this piece and put it here and I try and combine them, what do I get? They clash, right? Okay, so this is where a few things get really important. Curves have a direction, okay? So when I draw a rectangle like this, and this is the start point, 0, then the curve is going to be anti-clockwise, yeah? So the two vertical lines that we've drawn, what's interesting about them? One's going down and the other one's going up, yeah? So if I were to think relative to the one going down, outwards is to the right, yeah? And if I were to think outwards for the one going up, it's also to the right. Hang on, I'm trying to, let me, have I fucked this one up? The key thing here is, because everything's relative to the curve, instead of using a move, instead of using extrude, instead of using the idea of like outward and inward is a really good way of thinking of it, then instead we want to use the idea of offsetting, okay? So if you offset positively, we get an outcome that goes out, yeah? Have I fucked this up? I feel like I'm second guessing myself. Either way, that's what we have to do, okay? Now, this is a really, hello. Please go to the Moodle page and download the script. Also, those of you, like, try not to be late. Like, you know how I've said in the past, if you miss one class, you're screwed? It's almost like if you miss 10 minutes, you're screwed in a way, right? So just please be on time, okay? For your sake, cool? Because it means I'm gonna have to basically almost repeat everything just to get you up to speed in class. Okay, so this works really nicely for a box because when you have a box, you only need to extrude these lines or offset them by the width of the material, okay? If I were to then say, okay, let's take this shape and create finger joints between all the junctions. They're not 90-degree angles, so you need all this like very confusing trigonometry to actually work out how deep the joints need to be. And if you want a perfectly made object at the end of it, it's going to be difficult, okay? So we're going to struggle through this with a less than optimum outcome, Okay? Okay? Cool. So, in a box with edges, we know every edge needs a finger joint, right? But in this case, not every edge of these triangles needs finger joints. Right, so we need to actually work out which ones need finger joints. And we're going to work on this thing, fortunately, as if it was just one element. So, meaning there are 6 segments to this design, but fortunately they're radially symmetrical. So if you design one, then you can just laser cut that 6 times. And so if each component is 4, we only have to design 4 objects that just get repeat laser cut. Cool? Okay, so, I wish I could shut these people up. Okay, so what we now have to do is basically undo everything that we've done here to get us back to this stage, okay? And to do that, we just need to use brep explode. Actually, from last week, before we do that, we're going to use this thing called list item. I'm getting a really distressed face from you, man. Are you okay? You're like, ugh. Okay. So, who's not at this point? Right. Okay. If you're not at this point, then
Do I need the extrude point as well?
pardon?
Do I need the extrude
No, the extrude point's just to explain to them where we were last week at this point. Okay, so we've got 4 graph trees. They all go into a merge, which then gets brep joined and flattened. And please just copy this by looking, you don't need to understand what I'm doing, because there's some weird. And that is my cue to put this on airplane mode so it doesn't interrupt the recording ever again. Okay. So, you're almost there?
Yeah, which merge did you use? There's a number of them.
I used this merge. Really? There's another merge? Huh? The one that is merge. Only merge. Cool. No? Not cool? Not cool. So we've got graphed. Have you all got graphed? Okay, have you got merge? Have you got brep join? This is what I meant by turning up on time. Okay, and then flatten. Have you got flatten? So it's all come together now. Is everyone at this point, even those people who are shy, that aren't willing to say, are you at this point? Excellent. Okay, good. So, what we want to do is use list item. List item is very much like a picker, okay? So do you remember we had indexes last week for each student? So you were index 0, and you were index 1. Hello, Alienware. Hello, sorry. And then I know the class is shuffled around, but back corner, what index would you be? what index are you? If we put this as a class with a list, what index would you be? Without counting the number of people in the class, what index could you be? No, this person's 0. Huh? This person's 1. If I go backwards, if I go 1 to the right, so this is, if I go 1 right to 0, what do I get? And what would that make you? Excellent. Okay, so each of you have an index, right? So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so if I wanted to isolate one person, index 8, right? I could say pick index 8, and that would give me this person here with the blue glasses. No, with the blue tinted glasses, right? And the apple. I'll get your names eventually. Okay, cool. So what this component does, list item, allows us to pick one item from a list. It can actually allow us to pick more than one, but the point being, if I plug a component into that says 0, that will give me the first item in the list.
Sorry, what's the shortcut for getting the list?
Getting the panel.
Yeah, the panel.
If you double click, you can type double /
Okay.
enter, and that'll make a panel. Otherwise, if you double click and type 0, that'll also it'll give you a number slider as well. Like there's a few ways to do it. We've got a cat here. There's many ways to skin it. Okay, so we've picked out 1. That means we can sort of slow down a bit and just think about one thing instead of 6. Cool. Then we want to get this back into sort of like this surface.
Sorry. I typed in 0, fed it into I. But
Pardon?
I typed in 0, fed it into that I.
Yeah.
But it's just got a little red.
Do you have your flattened tree plugged into the L?
Yep.
And what if you highlight the little red thing? What does it say? There's a little red bubble. There should be.
Just come on. Red.
There's no bubble?
Not like it said, sorry.
No problem. Your solution's off. You've disabled the solver. So just to explain to everyone, if you're working on a script that you don't want it to compute every time you change something, you can disable the solver. So you can say solution disable solver. And that means that as you make changes to it, it won't compute. And that means you have to force it to compute. So to do that, you can press F5 and it will work, it will run, or you can just turn off disable solver. Okay, cool. Okay, so we've each picked out one item from the list, and we are then going to explode or deconstruct that brep. So you can find that under surface deconstruct brep. Holy crap, it's 9:41 and we're not even close. Okay, we're gonna rush. Cool, so what that does is once plugging that in, it breaks our surface down into our brep into the 4 surface elements that make it up, okay? So just think of it like this. Surfaces can't have folds or creases in them. So if you've got an object that has folds and creases, then it is going to be a brep. And if you deconstruct a brep, it will give you the surface faces, the edges as lines or curves, and the vertices as points. So we want to focus on the faces, so the 4 surfaces that make that up. Cool? Pretty simple? Okay, so then just to quickly get this back into the system where we're looking at surfaces 1, 2, 3, and 4, we're going to use list item again. So list item has this little trick in it that lets us basically move the data back into that format. So if I want, if I just plug in list item, something into list item, has anyone noticed that it already gives us an like an outcome, right? What outcome is it? It picks which one do you think? It picks the first one. So if we mouse over I, we can see that I already has the number 0 in it. So that's a default. There's a default that's programmed into that component. So if you quickly want the first item, you don't have to input anything. You just plug it in and you get the first item, okay? So as some of the students have noted before, this component here, we're able to actually bring in more variables than what it seemed like when we opened it. And if we zoom in, we can actually add and remove these components, these inputs to that component. Cool? So at the same time, if we zoom into our list item, you see how we get these two little black pluses? If I just press that once, what does it say? It says +1, okay? So do you see how we have the input is I, and the input is 0, so I is 0. So therefore, the I output is the 0 item, yeah? What do you think the +1 output would be? Yeah, so it'd be the second item, yeah? And so forth, I can click it 2 more times and get I, +1, +2, and +3. And what that should do is get me, like I can now basically get my surfaces back into, like if I just use this surface, parameter, I can basically get us back to the beginning. Hey, look, we're back where we started. In a way, kind of.
Do you want to do that?
Yes, please. Yeah. So we're going to do this the simplest way, the most beginner way. There are way more complicated ways of doing this that would mean less effort in the future, okay? I actually have a script that I built for work that miters timber elements together in any form of geometry. And it works well because I can put shapes into it and it just does it. But in this case, whatever we write here, there has to be some form of like critical thought applied to the outcome. So, for example, I need to create a finger joint between these two triangles, okay? The ones highlighted in green. Also, this triangle here would need a finger joint with its other neighbor, right? So right now, we are the ones that need to identify what neighbors this triangle has to work out where its finger joints need to be. Is there a potential third face that it would need for finger jointing? Yeah, where?
Along the right axis.
Along this line, right? Why is that?
Because there's another shape.
Because there's another shape next to it, right? So we got it? You get it? Okay. So, what is the easiest way for us to do this? In the past, we have I've shown this script to test for collisions. Like you show where it actually tests and analyzes to see where the collision is, but we're not going to do that. It's actually, we'll just do it through numbers, okay? Because it's skipping half an hour of teaching, effectively. I'll teach how to test for collisions in another lesson, okay? So what we're going to do is we're going to work on each surface individually. So let's hide.
How did you do that, sorry?
You select, if you select components, you can middle click or right click in the canvas and then select the blindfolded man and select preview off, and that hides things. Huh? Make sure you don't right click a component, right click the canvas and then preview off. And you can do the same with preview on. Huh? Yep.
How do you get rid of the whole shape, sorry?
So if you select, I hit Control A, which selects everything. You can deselect things that you don't want to hide by holding Control and then selecting them. We good? Excellent. Okay, so we're going to work on this surface, and we're going to get its edges, okay? So the way that we're going to get the edges is by doing a surface analysis. Under surface analysis, we can get BREP edges, and plugging a surface into BREP edges will give us the naked edges, the interior edges, and the non-manifold edges. In this case, this shape only has naked edges, okay? Any surface, and just purely a surface, will only have naked edges. A BREP that has joined edges will have interior edges. And if you've somehow broken the way physics and maths works, you'll have non-manifold edges, okay? So if you ever have a shape that has non-manifold edges, it won't be 3D printable. I don't know how you made it. You've made a mistake somehow. Congratulations, you made like a world-breaking mistake. Good job. Cool? Okay. Let me know one day if you do manage to make a non-manifold edge with a BREP. I'd be excited to see what it looks like. No, you can make them. It's just I want to see what you were trying to do to make it. It's quite fascinating what causes them. Okay, so we've got a list. Okay, we've got a list of 3 lines. Yeah. Now, without even necessarily caring about which one's which edges actually need to have finger joints on them? All of them, okay. Now this gets a bit weird, okay? This is panel A. We'll call it A1, right? So this guy here is called A, right? This dude here is B. Therefore, this panel here is B2, yeah? A1, A2, A3, A4, yeah? B1, 2, 3, 4. Okay, so we've got 1 and B2. And if we create a script that creates finger joints, we need some control over what is going in, as in what's going in and what's going out, okay? So we just need to be mindful of that. We can't just apply a blanket rule onto every edge. Some edges need to, let's say, be true with the first item going in, and some edges need to be false with the first item sticking out. Does that make sense? So, for example, the difference between these two edges are first item sticking out, first item sticks in, yeah? So we just need to be mindful of that, yeah? So this is going to come up later. What it does mean though is we have to work on each edge individually for a beginner, okay? So more work in terms of scripting, less thinking. No, I'm serious. Because there's some of this course is just about getting you guys to think in certain ways, and there are some massive mind fucks down the line, okay? There are points where I literally have to turn my music off and just shut people out of my life and just sit down and nut this, like, my problem out, and just focus on it. So we are going to ignore those problems for now and just get things, like, we're just going to work on the basics, okay? So this isn't the best way to do this, is what I'm saying. I don't think many teachers say that. Yeah? I'm going to teach you the worst way to do it first. Okay. So, we are going to pick out each line individually. Have a guess, how would I do that? If I want to work on the first line, what component would I do to only work on the first line? Exactly, right? So let's go get a list item. If we think into the future, we're going to work on multiple lines, right? How many lines are there per triangle? 3. So what does that mean? If I want a number slider that could potentially help me in the future, that goes from 0 to 2, let's make a number slider that goes from 0 is less than 2. Okay. How did I do that? Double click. If you type the number that you want to go as a minimum, and then a less than symbol, and then the number that you want as a maximum, let's say 765. Hit enter, that'll make a number slider that goes from that lowest number to the highest number.
What if you can't find your less than symbol?
It is if you hold shift and then comma. Unless you're using a European laptop.
No, but I have somehow set a keyboard to English, which I don't have done, but I found it.
That worked?
Yeah, it worked.
Okay, we have the same button at least there, right? Hopefully, you'd think the English keyboard would just have like the pound symbol instead of the $sign, right?
No, but put at in a different place, and that's why I did it, because it was annoying.
Right. Oh, because you're not used to the US. Yeah. Okay, well, fortunately, comma and less than is the same. Excellent. Okay, so what that does is it gives us the first line. Now, what is the first line? If we turn our base curve back on, the first line happens to be the edge connecting to panel B, yeah? So, let's work on this. We are going to now move back into the pseudocode, yeah? So we have a line. What do we need to do to the line? What was the word that I used? Shatter the curve. Okay, this is where a few of like little jokes appear in a Grasshopper. It's not a strong joke, but if you shatter a curve, so you can find shatter under curve in the divide, in the division section. Shatter takes a curve to trim, parameters to split at, and the shattered remains. Really weak joke, right? Tiny little weak joke. But there's some excellent humor in Grasshopper, I think. For example, check out the component that generates random numbers. What is it? There's a cat in the box. For those of you who don't know, Schrodinger's cat was an uncertainty problem where there was a random chance that a cat in a box would die, and while the cat was in the box, you would be uncertain whether it was alive or dead. So it would be both alive and dead at the same time before you opened the box up. Point being, there was a random chance of the cat dying, therefore random number generator. But my all-time favorite is the duplicate component. Which should be considered not safe for work. Okay. Excellent. I got some people laughing. It's good. Well, David Rutten's got some people laughing. That's good. Okay, so we need to shatter a curve, and we need to tell this. This doesn't actually care. It doesn't do it evenly. You can shatter a curve at any point. And this is where I start to have a little bit of fun. That had do not touch written on it. Oh well. Okay. How long do you reckon this is? 30?
400.
Let's say 400, yeah. I'm surprised I heard centimeters. Should be thinking in millimeters by now. Okay, so I can think of this object as a dimensioned length, yeah? So if I were to shatter it, pick a number between 0 and 400, and I'll shatter it. Any number, 200. Okay, so 200. 0 to 400. 200 is about there, right? So therefore, I would shatter it at that point, yeah? I think I went over this last week, but this is just a nice little example. We can think of objects as not just as dimensions, but as percentages, okay? From 0 to 1. So if I were to shatter it at 200, I would shatter it at 50 watt. Okay, and another way of saying 50% is 0.5, okay? Because 1 is 100 and 0 is 0. So 0.5 would give us that point there, okay? So just remember that objects can be represented as dimensions and also percentages, okay? So if we want to divide this line, we can create even numbers that go from 0 to 1. The key point being that for us to think of lines and surfaces this way, they need to be reparameterized, okay? It's a big word. Reparameterized, okay? I said it was big. Cool? So reparameterized means that we go from 0 to 1. Cool? So if I want to divide this thing evenly, what do I need to do? If I had the number 0 and 1 as a maximum, I just need to evenly distribute numbers that go in between those two, yeah? Cool? So if I wanted two elements, right, then I need to generate the number 0, 0.5, and 1. If I wanted 4, 0, 0.25.
0.5.
Exactly. Yes. Okay. Who thought that you'd be doing maths in a design course? Crazy. Okay, so there is this beautiful little component that generates numbers for us. I've shown you guys how to create series. Is that correct? Did I? No? Okay, don't worry about series then. We'll do series later. This component here, range, is a nice little component that effectively takes 10 o'clock. Come on, Andrew. It takes a range. Sorry, it takes a domain and it divides it evenly. So the default range that is in it is fortunately 0 to 1. Quite useful for us, yeah? Yeah? Quite useful, yeah? Because we want our number to be between 0 and 1. We're going to go back and change this later for a few reasons, but let's just stick with 0 to 1, yeah? Then the n value is the number that you divide by. Cool? So if we just grab a slider, let's plug into that 0 is less than 20. Then as we plug that in, you can't divide by 0. But as we plug that in, we get an evenly distributed set of numbers that go between 0 and 1, with the number of segments in between them being the number of corresponding to that slider. Okay? You're going to probably be using this quite a lot in the, because it is a very quick way to generate numbers, evenly distributed numbers. Okay? I'll talk about the domains soon. So if I plug my curve into shatter and I plug my range into the parameter, so the parameter along that curve, we need to just make sure that our curve is reparameterized. So to do so, we right-click the, yes?
I've got a data conversion failed from text to curve.
So just make sure you have your right inputs, okay? So what's the,
Yeah, I see what I've done.
yep, excellent, good. People can troubleshoot themselves now, that's good. Okay, so we just need to make sure that our curve is set to reparameterize by using these little shortcut widgets. So if you right-click the letter, you can then select reparameterize, and that will make sure the curve is thought of as 0 to 1. Right-click the C input, or if you're using the full display full names, then it'll be the curve input. This one. What does it mean? It makes sure the curve is thought of as 0 to 1. Okay. The way NURBS geometry works, these lines are actually infinitely long. And we're looking at a segment of that infinite long line at roughly like the coordinates. So it's saying, okay, give me this coordinate to this coordinate, yeah? It's then also saying that coordinate point is 0, and this other one might, like let's say this is 30 centimeters long, then that's at 30. And what reparameterize does is it just says set the start as 0 and the end as 1. Cool? Yeah. Okay, so we've shattered it, and we'll probably note that we don't see any change, right? Because if you break a curve up, but you keep it in the same point, it just looks the same, yeah? So just visually, we're going to grab the endpoints component, which you can find here under curve analysis. And we're only using the endpoints just to visualize this. But once I plug them in, what that does is it puts a point at the end of at the start and end of each curve. And so we can see that by shattering these and getting the start and end points of each curve, we have a divided edge, a shattered edge. Cool? Okay, yes?
When it comes to fabricating this, won't we want the shatter length to be the same as the depth or width of the material that we're cutting into? Because you want to
No.
finger joint.
No, finger joints the only thing that matters is that the extent that they extrude and offset either way has some relevance to the thickness of the material. The actual length of the finger joint doesn't matter. Yeah? So you can make finger joints that aren't necessarily square. You can make them long, elongated, rectangular ones. But you're right. Normally, when you're doing woodwork and doing finger joints, the best thing to do is make them square, because you then basically you increase the surface area for connection, and it makes a super, super strong joint. So we make boxes at work for massing, model making massings of buildings that are around as a context. And we use finger jointing for them, and we make them out of like 1 or 2 mil box board, and you can stand on them that's how strong the finger joint connection it makes them. So it really makes this a strong joint. So it's really, that's hence why, you know, you see it a lot in woodworking. Okay. So, by the way, I know when some people think of finger jointing, they hear dovetail jointing. We're not doing dovetail jointing, okay? Dovetail jointing means that you don't need glue. So as you fit them together, the two objects together, you effectively have to hammer them together, and the friction and force of the timber getting wedged together means that there's no glue required. We can't really do this here because we're using a laser cutter, okay? So we're not doing dovetail joints. Cool? Okay. So we've got the edges. Now let's think. We're back to this point. What did we do to our list? We're back at the point where we have a line and we have breaks in that line, yeah? And just to get people's minds jogging, that means we have items 0, 1, 2, 3, 4, 5, and 6. And we want to turn that into a finger joint. What do we have to do? Okay, so we need to dispatch them using a pattern, okay? What's the pattern that I want? Did you learn about patterns last week?
Yes.
Okay, good. Okay, so what's the pattern? What is a pattern that I can use to split odds and evens? -1 wrong, but yes, true, false. Okay, so if I had made the pattern true and false, what does true correspond to? Even. And what does false correspond to? Obviously. So true and false, we'd get all the trues. So true would be 0, 2, 4, and 6. Yeah? And so if we were to take all the trues and then do the process to them, we would get a result like so. Yeah? Cool? Does that make sense? Okay, so let's use dispatch. Let's grab a dispatch. And we are purposefully going to define the pattern here. We're not going to use the default. So let's say true, the evens are going to be true. So we'll go 1 and 0. Because remember, Booleans, trues and falses can be understood as true, false, or 1 and 0. So it's just a quicker way of typing what we want. It's a universal language thing as well. So if I'm in Finland, I can say 0 and 1 and they'll know what I mean. Cool. So if I plug my shatter into the dispatch and we plug our 0, 1 pattern into the P, those of you using Mac, just let me know if that breaks. Doesn't break? It's broken. You might find that it breaks if you have something in, just remember when you write into a panel, you need to right click the panel and select multi-line data and turn that off. And that will then give you a line, like a new item per line instead of a single object. Are you guys, you're okay? Good, okay, thanks for turning up. It's going to take me too long to catch you up to where we are at the moment, okay? But it's being recorded. Cool? Excellent. Okay, so what that means is 1 corresponds to A, or true corresponds to A, and false corresponds to B. So all the elements that we want to work with are going to come out of A. So if I just quickly grab a geometry or curve parameter, then we can highlight, can you see in green the highlighted elements that we want? Excellent. Okay, so now we're going to offset them, yeah? So we need to offset a curve. Now, this is where Grasshopper really helps us not be ignorant. So if I go grab an offset curve, actually, let's not grab offset curve. Let's grab offset curve loose. In theory, how many parameters do you need to offset a curve? Have a guess. Huh? You need a curve. And what else? The what? Well, when you're drawing in CAD, everyone here uses CAD? No? What do you use? You're a project manager.
Yes.
Okay. Same as this guy. Okay. Just consider this, okay? If I draw a circle and I want to offset it, right? If I were to use a CAD package, I'd click the circle and then what do I need to type in? What do I need to give it? The distance, right? Or the vector is, you wouldn't use vector because vector is, every direction, right? Like you'd have to give it every single vector. But with an offset, you just give it the distance. So let's say I want a 10 meter wide road. I take my curve and I'd offset it 10 meters, yeah? Yeah? Okay. But there's actually one other parameter that we forget about when we're normally working in CAD. And if I just move my mouse, do we just have a note, the offset loose component, how many inputs does it have? 3. So what's the first parameter? Yep. You can mouse over these and they'll tell you. Yeah. What's the second parameter? And the third parameter? Plane, right? So most people take for granted that they're working in 2D. Are we working in 2D right now? We're working in 3D, yeah? But you can only offset things in 2D. Like curves, you can only offset curves in 2D. Any other, component that reckons you can offset not in 2D, it's not really thinking offsetting, right? So, which plane are we offsetting in? Huh? No, you're not. Well, that's not a plane. XYZ is not a plane. It's not a straightforward answer, right? You don't need to give me the exact number of the plane. What plane are we offsetting in? Just use, you can use words.
Surface.
Yeah, the surface of what? The triangle. The surface of the triangle, right? It's planar, yeah? And we need to offset relatively to that, yeah? So that means we need to analyze it to get its plane. Everyone familiar with planes? Do I need to explain them? Not aeroplanes? Not the things that you use to thin wood down? Planes, P-L-A-N-E, mathematically, they are an infinitely flat object that exists in space. They have, in this case, they have an origin. So, for example, the Cartesian plane that we all, did maths on, graphs, is X and Y. That is a plane. Anything that we draw in plan view with project on or heights off is on the XY plane, yeah? Okay, so we need to work out where this plane is. So we need to analyze our surface. We need to evaluate it, or we need to test for its planarity. So if we go to surface, look under analysis, see if you can find a component that has any relevance to planarity or planar. We're working on a surface and we're working with planes.
Evaluate surface.
Yeah, that's one way of doing it, but think even look for the word plane. Yeah. There is a component in here called isPlanar. Cool. You could also use evaluate surface. You're right. But is planar just much easier? You just plug the surface in, it gives you the plane. Cool? Okay, so if we go grab the surface that we're working with, which happens to be this guy, what we're going to do is just copy that surface parameter and bring it forward so that it sort of sits in this environment a bit better. Whew. Okay, we can do it. We're going to plug our surface into isPlanar. isPlanar is going to give us two results. It's going to tell us, yes, true, it is planar. Excellent. Good. We haven't fucked up somehow. Good. Okay, but as well, that wasn't a question. Good. Okay, that was a yawn. The second thing it gives us is that the plane that it exists on. So we can now take our curves. Pardon? Yeah, that is the grid is a plane. So just so that you can see, you probably have something that looks a lot like this. Okay, that is Grasshopper's representation of a plane. Okay, so planes are an infinite object. So instead of drawing an infinite object, it just draws a little grid object to represent it. Okay, actually, Christina keeps changing the display properties of Grasshopper. I'm just going to do this because it frustrates me. There we go. Okay, so we should get this little red grid with a green line, and there should be a thicker red line as well. Yeah? And those two just represent the X and Y, or the U and V directions of the plane. We're really going to get into some maths. Like, this is super maths. I know like most people were told they thought that maths was going to be like useless to them for the rest of their careers. You know, once you get out of year 11 or 12 maths, it's like, well, I'm not doing engineering, and I know how to use Excel to add two numbers together and divide. That's it, right? All that geometry that you learned in high school is going to come back to haunt you in this class, okay? So the good thing is the computer's going to do all the computations for us, and we're going to be doing all the sort of fun stuff and actually deciding how to use it, okay? So this is the plane. If we use this plane as the P input into the offset curve, loose, and we use our curved geometry to go into that, then if I just quickly turn my dispatch on, you will note that we will get an offset off that curve. And with a number slider, we can change the depth of it. So what thickness material are we using? 3 mil. Okay. Now, if we were using 3 mil on a 90-degree orthogonal joint, what depth would we need for the finger joints? Exactly. If we were to make it 45, boom, 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 is it going to be more or less than 3 mil? More. Okay, so let's just guess. Let's say that we need at least 6 mil. Okay? So we're going to go 0.00 is less than 6.00 because we want some decimals. And that's going to give us a number slider between 0 and 6 with 2 decimal points. Okay, I'll type it again. I'll put a panel in just so that everyone can see. 0.00 is less than 600. No, 6.00. Cool? Whoop. Cool? Excellent. Okay, so we're going to use this slider. This is actually going to control more than just one joint, okay? So this is going to eventually apply to more. So we'll put it off to the side, up the top, plug it into our distance though, and we can see as we slide this in and out, we get our finger jointed elements sliding in and out. Cool. Next step. This is the interesting thing. This is where like we got to think in reverse, okay? just think in reverse. I've got two lists, okay? I've got a list A and a list B, 0, 1, 0, and 1, okay? And I need to bring these back together again, yeah? Because we want to think about things as one list in Grasshopper for them to work quickly. So remember last week how we connected a point from 0 to 0, like so, right? But the thing is, for the 0 on list A, we need the end point, and the 0 on the list B, we need the start point, yeah? To actually connect them up. There's a quick little component that does that called connect curves. So what connect curves does is it takes a list of curves, it looks at their start and end points, and it connects them. Cool? But we need our curves to be in the same list for that to happen, okay? Now, we've used merge. I didn't really explain what it does, but what merge does is if I consider you guys as one list, right? And I consider the yellow sweater crew here as another list, right? So 0, 1, 2, 0, 1, 2, yeah? You're in your own separate lists. If I merge you two and I put these guys first, we get 0, 1, 2. What do you reckon your index is? Yeah, 3, 4, 5, yeah? If I put you guys first, we get 0, 1, 2, 3, 4, 5, okay? We don't want that, right? Because if I have these two lists and I combine them, that would make 0, 1, 2, 3, yeah? Which means if I use this function on it, it would do that. Okay? So what we want to do is use the opposite. I keep getting like such worried looks from you. You're just like, fuck this, fuck. Okay. You're my gauge, you're my compass. I'm like, okay, I gotta slow down. I'm getting the face. Okay. It's good. Don't stop it. I like it. It tells me to slow down. Okay. So instead of, what did we do? What does dispatch do? Yeah? Don't have some confidence.
Divide into two lists.
Divide's probably the wrong word. It separates a list, single list, into two separate lists using a pattern. Yeah? The opposite of dispatch is weave, which takes two lists and weaves them together using a pattern. Yeah? So if we were to have two lists, if we were to have two lists and we were to weave them back together again, give me a pattern that would make them weave together the way that we want. So what number do we want this to be? What number do we want this to be in the completed list? 0, right? Then what do we want this one to be? And then this one? You get it? Okay, so what's the pattern? If I say this list is A and this list is B, give me the pattern of how I weave them together. So A, then B, then, yeah, then. Do you see a similarity to anything? Right, let's turn A into true and let's turn B into false. So, what is the pattern that we need to weave them back together again? True, false. That's it. That's all we need. True and false. Is there anywhere we've written this in the script? Where do we use it? Right. Okay. So, the dispatch pattern that we use to separate them can be the exact same pattern that we bring them back together, right? And we know that true corresponds to 1 and A, right? So therefore, if I grabbed weave now, we can see in the weave component, there's a pattern, there's 0 and there's 1. So 1 corresponds to true. So if I plug my pattern in, my 0, 1 pattern into P, what needs to go into the 1 component? The 1 input, sorry.
The offset.
The one that we offset, because the ones that we offset were the ones that were true, right? Yeah? And so the others, the guys that are coming out of B, they slide into 0, okay? Does that make sense? I think this is probably like the most important thing about this class right now is that we've made a correlation between trues, A's, and what we do to them, and then we're going to bring them back into this exact same order that we had them. So trues go back into true, and falses go back into false. Okay? Cool? Excellent. So let's plug our offset curves into 1, and let's get the curves that have come out of B and plug them into 0. And we still don't really see the order that they're in until we use this component. So I'm going to hide everything. I'm going to preview the weave, and then we're going to use connect curves, which we can find under curve spline. And we just quickly want to turn, It's called connect curves. Can you read the top of the? You can see that? Okay, good. So I've put on this thing called bifocals. It just tells you what the component's called. So if you, if I've just been a bit too quick with it, you can still find it. Cool. So what connect curves does is exactly what I explained here, although the defaults that it uses aren't what we want. So what we need to do is select, we need to put the number 0 into the G, which means that instead of connecting our curves with splines, it connects them with straight lines. And we also need to turn off the closed loop. So we need to put another 0 or false into the L, and that will then create our little finger jointed line. Does everyone, once we've done that, does everyone sort of get where we are?
Which component are you linked to the 0 and 1 only wave?
Pardon? So if you mouse over G, if we mouse over G, it tells us the continuity of the blends has 0 equals position, 1 equals tangency, and 2 equals curvature. You don't need to understand what most of those mean. We just need to know that 0 means it's going to be straight, okay? So that's why we're putting 0 in, to make the line straight, yeah? Then, this component also allows us to close the curve up, yeah? And so if we put a true into the L input, then it will create a closed curve. Or if we put a false, it won't. And we don't want to close this curve, okay? So that's why we've put 0 into that one as well. Because 0 also means true. No, it's a joke. 0 also means that is correct, that is true. Okay, so the cool thing here is you've now got a script that you can use to create finger joints on whatever you want. Okay, so you go and do some work at the in Studio now, and you need finger jointing. You've got a script that can effectively create finger joints of whatever division across the line and with whatever thickness okay? We're not done. We've made one line, okay? We've made one line. But we've made it in a way that we can use this on other curves parametrically, okay? So this is where Grasshopper gets really useful. I've made a component that finger joints a line, which means I can use that same script to finger joint other lines. So this is where we're going to just use a little shortcut that Grasshopper's made us to copy and paste things, okay? Because we have to imagine copying and pasting as something that's bad, because if I do one thing to, like if I had twins, right? And I dyed one of their hairs a different color. Like for example, let's say these two young ladies are twins. I know you're not, okay? And we've got, your hair is dyed, right? If I dye your hair, her hair doesn't change color, yeah? But sometimes we want to set up relationships where that happens. Okay, who here's used blocks in CAD packages? Except for you guys. No one's used blocks? One person? Never used blocks. Who's used families in Revit? You've done that. Okay, so we can think of blocks of code in Grasshopper like families in Revit or like blocks in CAD packages. So who's not familiar with blocks or families? Everyone's familiar with blocks and families? No. Okay. If I were to place a chair block, let's say I'm working in a stadium, yeah? Which happens a lot for me, not to show off. Let's say I place a chair block, yeah? And I place 80,000 of them, okay? The beauty of the chair block is that I can go into the block a year down the track and change how it looks, because let's say we've actually decided on the product that we're going to use, the chair product. And by changing how it looks, so let's say we've decided that the chairs are going to have armrests because the client's found a little bit of money and they've decided not to pocket it and actually give it to their customers, okay, to make more money. So by me changing one armrest by one chair, then that will roll over to every other chair that's placed, every other block. And that happens with families, right? You edit one family in Revit. If you've used that same family elsewhere, it changes. Am I on the same page with everyone now? Okay, we can do the same thing with Grasshopper. So we can turn a collection of components into a cluster, and if we change one cluster, it will have a rolling effect to every other entangled cluster, okay? So we consider this as like entangled, they're entangled, yeah? Entanglement. Cool, so clusters look a lot like components. And before we do anything, before we actually make a cluster, we actually need to be really sensible about it, okay? We have to think about what the inputs are and what the outputs are. I know I've just gone on a massive tangent, it seems, but you just need to consider this, okay? We're going to copy this script and use it for the next line, okay? Don't do what I'm doing. Don't do what I'm doing. We're going to copy it, but imagine how many lines are in our component, our like full thing. There's three lines per panel, and there are 4 panels. So that means we need to produce 12 of these, yeah? And if we made 12 of these, it's going to be an absolute mess. Yep. So what we're going to do is tidy it up and make it a block, make it a cluster. So what is the common thread? What are the common inputs for each of the components, each of these lines? Each of them needs to test whether or not it has a surface. Each of them needs the list item component. So the list item takes a curve, right? So what I'm going to do is place a curve parameter in, and I'm going to disconnect the list item from the Y that goes into list item and plug it into curve. The way I did that was I held Control Shift and I grabbed the wire and I can move it while I hold Control Shift. Huh? So I'm holding Control Shift or Command Shift. And I've moved that into the curve component. Then, this number slider, is that going to be different per each section? What does that number slider do? Do you remember? Okay, you don't? It picks the line. Yeah. Is there any other way of doing Control Shift? No. Are you sure you're doing Control Shift? Control Shift, and then you can pull. Yeah, excellent. Okay, so what I'm doing, guys, is I'm actually basically just visually separating some of the elements that are going in. Like if we were to sort of create a block, like an actual group here, what I'm doing is just laying out which components sit at the beginning. What are the inputs? What are going to be the inputs of our system? Okay? So the number slider is going to be unique, so we're actually going to pull that out of the block, out of that purple zone. We're going to plug that into an integer parameter, just to keep it nice and neat. So what we want is all the inputs that go into our script to sit on the very left, and we want all the outputs to sit on the right. So what's one of the outputs? The only output is going to be the curve. So what we'll do is we'll get this curve component, plug it into a curve, and just a little trick, we want a second one, okay? So the second one is going to sit outside of our block, and the first one is going to sit inside, like so. By the way, this purple thing is just a visual representation. I don't expect you guys to create this group. You don't have to do that. Have I missed anything? Is there one other input that might need to be pulled out of the component? Everything that's purple is going to be inside, everything that's not purple is going to be outside. Have I missed one? Yeah, and do you remember what this slider does?
That's the size of the joint.
Yeah, do you remember it's the thing that defines the depth of the offset? Okay, so we're going to pull that one out as well. So I'm just going to remove it from the group. And as we remember before, we need like a little parameter to sit on the left. So we're going to plug that into that parameter. So, and if I hold Control Shift, I can slide that over so that it sits within. Now, you can be really organized here, guys. If we go through and right-click each of these parameters, right? So if I select the curve, right-click it, and I type FJ curve, finger joint curve, then select the little paint bucket. See how it's named it FJ curve? Okay, it's just keeping it nice and organized, yeah? So I'm going to go through, call the first curve FJ curve. The second number integer is the edge index. I'm going to use all caps. The third number is the distance, the material, the FJ depth. And the last is the surface. Okay. So in doing so, is everyone finished naming their parameters? You don't have to name them exactly what I've named them. You can name them whatever you want. the reason I'm making a big deal over this is making clusters. It's not straightforward. You can't just select everything and just say make it a cluster. Just think about what you're doing when you make a cluster. Organize it, then select everything inside the system. So we don't want to select the very last component, and we don't want to select, we want to select sort of like these organized inputs. Once doing so, we can right click or middle click and select the box, which then parcels that all up into its own clustered component. That happens so quickly, right? Okay, I'll undo. So we select, we right click in the canvas and select cluster, or middle click and select the little cardboard box, and that'll parcel it all up. It's almost 11. We've got such little time to finish this. Okay, so what you'll notice is this still runs, right? It still works as if we've got that code working, but we've now the code's kind of like in this little component, right? So if we want to check on the code, we can double click and it'll open up like a separate area which actually has the code that we wrote, okay? So if I just save and close, so if moving in and out of clusters, the little box up here, the cluster box, if you click that and then select save and close, that'll take you back to the main document, okay? So now, if we just keep our finger joint depth separate and we copy this component and we change the edge to 1, we've now generated a finger joint for the second edge of that same triangle. And if we copy it a third time, we create a third finger jointed edge for that triangle. And if we change the slider for the width, then it changes it for all of them. Does that make sense? Yes, no? Okay, so if I double click into my one of those clusters, do you remember, see the range, how we divided by 20? Yeah? If I change that now to 10 and then go back, that's now set to 10 on all of those components, okay? So anything that you do inside the cluster is going to get duplicated to each of those components, and anything that we do outside is technically unique, okay? Are we all good? No, you're not good. What's happened?
You got 4 items for the block, but we only have 2.
You only have 2. Okay, so if I just undo, so just, do you have these 4 inputs? Do you have the finger joint curves that go into the list item, the edge index, which is a number slider that goes into list item, the finger joint depth, which is the number slider that goes into the offset, this one? Who's this lady? I've never seen her before. Hello. Are you here for Beil 0015? Okay. Are you completely new? So you haven't been to class yet? Were you last week? Were you here last week? Were you in my class or Christina's class? Okay. Sorry, I'm just face forgetting. Yes.
Whenever I put it into a component.
The cluster.
Yeah, the cluster. It disappears on the screen.
Okay, that's fine.
Oh, cool.
Yep, that's cool.
So what components again you're putting in?
So I have the curves that go into the list item, the index that goes into the list item, the depth, which is a number that goes into the weave. Now, for depth, for these, just remember I've used curve. So I've used curve, integer, number, and surface. But we don't have to use those, okay? We can just use this component, data. If we use data, then it doesn't matter what we plug into it, it doesn't care, okay? So just, if you use data, then that prevents you from breaking the whole script.
Sorry, what the number go into?
This number,
Yeah.
it goes into the offset. It's the number that we use for the offset.
Yeah,
Yeah?
that's right.
That's correct. And then the last one is the surface, which we plugged into the isPlanner.
Yeah, it's all connected to the right.
It's all connected.
Yeah, but when I block it, it's only have the
Two. Is that you need to select
all of the
all of it?
yeah, exactly.
Okay. This is strange. Do you have things going into those though? Like the components that you've.
Oh, yeah,
It's working now.
yeah.
Okay.
So I will to finish
I get it. Oh, good. Cool. So, are we all, those of us who are following along, are we all at this point? No. Where are you at? We're only halfway through, but by the way. No, I'm serious. Like, this is the hardest class. I was being serious when I said that.
Do you just simply add onto the cluster?
Yes. Is you don't have an output? Yeah, you need to make sure. Undo. Guys, this is just make sure that you've got the very last item isn't selected when you cluster it, or otherwise it's going to be that is going to be included in the cluster, and so the cluster doesn't think that there's going to be an output. So you need something leaving the cluster for it to be able to cluster and have an output. Does that make sense?
So that's after the
Yes. And if you put 2, you can select like up to the second to last one, not the last one. Where are you at,
Is that
man?
how it should be? So I've got this one goes
Yep.
into isPlanner.
Yep.
That one's going into the edges.
Yes. Yeah, but you've kind of gone a bit beyond what we need to do. We want to do this. Fuck, why don't you have a mouse? Okay, that works. So this we don't want in the cluster. That's the surface that's going in. So if we just create a component called curve, a curve component or a data component, and plug that into the data component, and then plug that into the list item, and then you're good to go. You good, man?
Well, like I was saying,
Just be careful, guys. Be really careful about what you select before you cluster, okay? Let me just be really forceful about what I'm selecting.
And can it be like this? Instead of like class on, like different, like integers going into, because this
Sorry, what are you saying?
because when I did the edge index,
Yeah.
like I want all three of them.
Yeah, that's what you're doing.
That's what I'm doing.
Perfect. Okay, guys, look, just to be really forceful about what I'm doing, I'm not including this. This is going to be an input that goes in, and so is the surface. We just want these four, and you have to be really careful about what you select, okay? You select it, cluster it, you should be good. So just being really mindful about what you select. Okay, I gotta move on, sorry. Okay, so I'm gonna copy this 3 times to work on the 3 separate edges. So I have edge 0, edge 1, and edge 2. And that gives me the 3 edges of the triangle. Now, if I were to take this straight to the laser cutter, it wouldn't work, right? Because by finger jointing,
Sorry. How come yours aren't joined up?
that's what I'm just explaining right now.
Okay. Mine are joined up.
Huh?
Mine are all joined up.
I doubt it. They collide. Ah, yeah, okay, that's because if I set this to an uneven number, no, that shouldn't work either. Really? How does yours join up? Either way, doesn't matter. What we're about to do is explain how to make them join up, okay? Because there's something that yours is doing that's still going to make it break, okay? So these don't join up, and as well they don't, when we actually start looking at the other triangles, some elements are still going to collide because of the way 3D geometry works. Especially like as we set this off in this direction, as we try and join these up, this thing's going to get super long, right? It's going to be much bigger than what it should normally be, yeah? So first thing we're going to do is we're going to double click into the cluster because we need to make some modifications, okay? Our finger jointing doesn't actually, we don't want it to start on the 0 to 1, okay? Because like they're the ends of the line, yeah? We actually want it to start like a little bit in and just leave some like clean straight lines near the ends, okay? So the way that we're going to do that is we just need to change the numbers that our shatter is using to divide at, okay? So right now the default output input of the range, I have to be really quick here, guys. We've only got an hour left. Okay, here we go. The default input is a range. Ranges are objects. So a range describes 0 to 1. I'm going to put in the component construct range. And because we're in a cluster now, we don't have bifocals. Okay. So I'm going to put in, construct domain. And what construct domain does is it sets a minimum and maximum for your range as A and B. And so if I then plug that into the range, we can see as I slide the low number up and down, it changes the location of where it starts, and the high number up and down, it changes where the finger joint ends. Cool? Okay, so just to be really nice and OCD and like equal, if I create a maths component expression, and in that I type 1 minus x, what that means is, when I plug a number into that, it will take that number and subtract it from 1, which means the output of it, if we plug into B, will then give us a nice little balanced outcome when we chuck that into a number into the range. Okay, so it's just saying take 2.57 from 1 and make that as the end one. Cool. How do you make an expression? You can find expression here. Double click it. You can go type 1 minus x into it, And then you can get rid of the Y by zooming in and clicking the negative on the Y. Those of you who are using display draw full names, turn that off because it's going to screw you up. Or you're going to have to select your component, right-click the X input and type X into it, or otherwise it won't work. That's you, I think. That's you. Red jacket. Do you want to show it? So basically, if you have this on, if you've got this thing called draw full names, do you have that on?
Yeah, I took that too. No.
You turned it off?
Yeah, but
Okay, good.
like
Sorry, how do you make it do decimals on the slider?
When you double click, type decimals into the number so that it actually, and the more decimal places you put as you type, the more it'll put in the slider. Cool? Okay, I'm going to just keep moving, guys, because we've got an hour. So that is one. So that allows us to control the extent of the finger joint. Then we just need to create a extended curve. So if we at the end, before we just at the end after connect curves, we're going to plug that into this component extend curve. What extend curve does is it basically lengthens the length of a curve. If you put a number in, so if I type in 50 as a number slider, if we plug a number into L0 and L1, location 0 being the start and location 1 being the end, then it will lengthen your line by that number on both sides. So as I slide this up and down, we can see our line is getting longer by that number. Cool? No, not cool. We're doing this at the very end. We get using the curve extend curve, the component extend curve. And then we're going to plug that into curve instead of the connect curves. And so that extended curve will be our output.
Shouldn't be the
Huh?
number slider be the outside?
Pardon?
Shouldn't they?
No, let's keep it inside. Because it'll apply to all of them, right? All of them are going to be extended. Yes, that was a question?
My expression
Your expression
turns red.
turns red.
Yeah, and the connect curve at the end.
Okay, well, is everything red?
So the expression and the gray line connected.
Okay, if it's turning red, just quickly, instead of using the expression, you can use the component subtract. So you can go get subtraction under maths operators, and you can plug the if you put the number 1 into that, that's the equivalent, and this is the equivalent of writing that maths expression. And then your curve at the end is red. Is it? Is that because you need to put this number slider into both L0 and L1? You did, and it's still breaking? Hang on. Zoom in here. No. Remove all of that. Delete, select, no. Undo, double click it. Type into all of this, one minus x. Yep, okay. Yep, cool. So that's working now. Hang on. Zoom in, come back here. No. See this number? 10.
So that will be 0 to 1.
Yeah,
Okay.
it can't be 10, but so this might be why. Cool, and then just make that 0.25 or something instead of 1 because you're just going 0 to 1. Cool. So keep this guy here. It's not the right one. You need construct domain.
Yeah, I think I select this one.
This one. No, one below. Keep going down. This one.
Okay.
Yep. So that plugs into A, R plugs into B, I plugs into D, and now,
That one.
may I? Sorry. I've ruined your glasses. I broke them. Come on. Gotta be quick. Okay, it's
That's
working.
because the number.
Yeah, it's just some. Okay, some of them are gonna break. Okay. Okay, guys, gotta be quick. Gotta be quick. I'm gonna basically say if you can't follow now, it's fine. You just go back to the video, okay? So we've extended the curve. Now if I save that, we can see that these are all. Some of them are fucked for some reason. Why is this screwed? Let's set that to 10. Okay, so we've got extended curves here, and they're all getting finger jointed. Now there is one extra thing that we need to consider. All of these are finger jointing with the pattern true, false, yeah? But sometimes we might want them to not Sometimes we might not want them to finger joint with true, false. We might want them to finger joint with false, true, right? Because if I take the line that this joins to and I use this script on it, then they might collide, yeah? Like the way that I showed before. Do you get what I mean? So we just need to create one more input that goes into this component, which is this input. So one way of doing that is after going into the cluster, if you go to utilities, there is a cluster input component. If you place that into the script, bring it all the way to the bottom and plug that into either a data or a Boolean function. Let's just use data for now. Rename it as pattern. And then we're going to Control Shift drag our wires into pattern. What that does is it now creates an input outside the cluster called pattern. So now if I save that, we can see here. Huh? When I dragged it into this new pattern thing that I created. They were connected to this. They were connected to this thing that was connected to the dispatch and the weave. Okay, so what that's going to do is create a new pattern input, which we can use to plug our patterns in. So that means if you can recognize that this needs to be swapped over, this edge, then we can instead use the 0, 1 pattern. And so now if I plug that 0, 1 pattern in, you'll recognize that that finger joint flips. Okay? This is important for making this thing. If you don't put that in, like as we work, you're gonna see that these edges might not line up. This is the way to make them line up. Okay? Does this all make sense? Do you understand why? It's like this. My fingers don't line up, so in a way, I have to shift, like I have to flip the pattern, and therefore that then allows them to actually join. Otherwise, if the pattern is the same, then they might clash. It's as simple as that. Okay, excellent. Let's keep moving. So for now, let's just use. I'll leave it as is for now, so that we don't get lost. Okay, so we're on the home stretch. We've got an hour left. We need to trim this thing. Trim it good. Okay. So there are 3 edges to this that need to be cleaned up to create like a closed shape. Because at the moment we've got 3 curves that are all separate. And we don't want to laser cut this because we're going to waste material laser cutting it, yeah? So what we need to do is get them to trim each other. I still can't believe how complicated this, like we're at week 3 and it's like the most complicated thing that we could get you guys to do. Okay, so the way that we're going to do this is I want a cheap way to do this. I want the cheapest way to do this. Cheapest as in time-wise. Okay, I got it. Okay, so what we want to do is we want to merge these back into a single list, okay? The reason I'm doing this, the component I'm going to show you guys is this guy. It's called, the curve self-intersection component. What it does is if it, for example, this shape that I've made here, it self-intersects itself. We know that it self-intersects itself here and here, yeah? So what I'm doing, did I erase this? No. Okay, whatever. What I'm doing is I want to quickly work out where this thing self-intersects, but I have to make it the same object, yeah? So what I've got is 3 curves, like so, yeah? And I've already taught you guys about the component that connects them, yeah? So connect curve would create a shape like this, yeah? And in doing so, by making a shape like that, it self-intersects. It self-intersects here, here, and here. And by doing that, we can create like a test pattern that then shatters this curve at that parameter, and then we can dispatch and remove these elements of the curve. That's what we're doing. It's plain and simply really difficult way of thinking about things, and I'm sorry that I'm rushing through it, but it's just a really quick way of me getting you guys to actually produce a finger-jointed candela surface, okay? So, what we're going to do is we're going to merge our 3 lists together. So we've got 3 curves. We're going to merge them, 1, 2, and 3. And because as long as we're doing this in the right order, as long as we go 0, 1, and 2, therefore 0, 1, and 2 going into the merge, when I use connect curve, and I set the G to 0, that looks like it could work. What it does is it creates a self-intersecting shape, okay? So now, if I plug this into my curve self-intersection, it works out at these points here, those are where the curve intersects itself. And so the output of that are not only points, but parameters, okay? Do you remember reparameterize? So if I reparameterize curve as it goes in, instead of giving me dimensions as an outcome, it gives me percentages. So at 0.98%, it self-intersects, and at 10% it intersects, and at 26% it intersects. Yeah. Have we used any components that breaks curves up based on their parameters? What was it called? Right. So we can shatter our curve using these parameters. Let's do it. Let's go grab shatter. Let's plug our curve in and our parameters. And what do we have to do to the curve? We're working with percentages, so what do we have to do to it? We're going to reparameterize the curve. That gives us 5 separate curves. And now if we dispatch these curves, because Fortunately, the self-intersection pattern is like a alternating 0, 1, 0, 1 pattern. That means our curves that we want to keep come out of the A output, which means if I hide these guys, that leaves us with a nice little clean triangle. I know I just did some weird brain fuckery there. I get it. But basically, this is kind of like how you become a master of this type of thing, is knowing what the components do and how to, like, what steps to take to get something really quickly. I know, like, I did something in a really weird way. I was like, okay, let's take this curve and this curve and this curve, we could just find where their ends are and get the subcurve in between. Instead, I said, no, let's connect it all and find self-intersections and then shatter and then dispatch and then take the alternating dispatch. But what it's done is got you all a nice little short script there that gets you the closed triangle. Okay? Not quite yet.
When I select curve, it just selects that one over there.
Huh? Just hide everything but the output now.
Oh, okay.
Okay, so these curves are not joined yet. So let's join them to create a nice closed curve. So we use join curves.
No, that's not working.
Okay, I'll be back in a sec. I'll just get everyone to join them. You also don't have a mouse. I suggest you get a mouse, man.
Yeah, I forgot it.
Okay, you didn't reparameterize it.
Oh, I've reparameterized what I'm saying.
No, we want to reparameterize both, which gives us that.
Beautiful.
Brilliant. Cool. We've joined the curves. Yep. Okay, so one last thing. Yes.
Curve cell.
Pardon?
Curve.
This curve self-intersection. Where is it? You want to know where it is?
Yeah.
Or you don't?
I just.
You can't find it? You can find it here. Under intersect. Oh, this lesson covers way too much shit. Okay. Good? Okay, so one more thing. This, I know this is going to happen, so that's why I'm warning you, but you might end up discovering this as you work along. The extents of our triangle actually are going to clash with other triangles, okay? And so one way of getting away from that is actually just by chamfering them. And actually, so in our final thing, there's going to be some holes at each junction, and we just need to chamfer that. Quick and easy way of chamfering is by trimming with circles or cylinders, okay? So we're going to go back to our original surface, our original B-rep, and we're going to create some cylinders to trim with. We'll do it. We'll get there. You look, you've glazed over. You've like,
Oh, I just watched the video.
okay, this is too much.
I was going ages ago.
Okay, so in our deconstruct B-rep here, fortunately, what that's done for us is not only created 4 surfaces, it's also generated edges and vertexes. The vertexes are the things that we want, okay? What we're going to do is we're going to transform them. We're going to flatten them with project, okay? So we're going to take our vertexes from this deconstruct B-rep, plug them into project, and that's going to flatten them onto the ground, okay? Because these points are then going to generate cylinders. So from that point, we are going to create under surface primitive, there is the cylinder component, which takes a center point and a radius. I'm going to create a radius with a number slider. You can decide however much you want. I'm going to say, let's say 0 is less than 200. I'm sure 200 is too much. And that will then allow us to change the radius of our cylinders. And you can see what my intention is going to be is I'm going to use these cylinders to trim the triangle. Okay? So cylinder goes to a certain size. Then we also want our cylinders to have height because they need to be 3D to trim our triangle. So we're going to create another slider that goes from 0 to, let's say, 1 meter, just to guarantee that it's going to get everything. And we'll just pump that up. Oh, shit. And one other thing, we just want to make sure that some of our curves could actually go below the ground at the moment. Like if I just quickly show you, if I offset this triangle, right, outwards, then the edge is going to go beyond the ground, yeah? So we actually need our cylinder to be lower than the ground for it to be able to trim that triangle, yeah? So what we're going to do is we're also going to place a construct point. In the construct point, we're going to place the length of the cylinder into Z, but we are going to right-click Z, select expression, and type minus x divided by 2. What that'll do is it'll take the number 1,000, halve it, making it 500, and then make it negative. So it's going to be negative 500. What that'll do is it'll place a point at the negative 500. If we plug that then into the project plane, it will project our points to that location in the Z. And then as we run the number slider up and down, it will effectively center these extruded cylinders on 0. Okay? So it just guarantees that we've got a centered cylinder. We then need to cap the cylinders because they need to be solid. You can see that they've got holes, you know, they're empty. So this component here, cap holes, will take all planar holes and put a surface across them, creating a solid B-wrap. This cap hold B-wrap is the B-wrap or geometry that we want to use to trim our triangle. So we are going to take this output, pull it over to the right here with our joined curves, and it is the thing that we're going to use to trim the triangle. So let's just hide everything but the triangle and the cylinders. So what I might do is just set my cylinders to be a bit smaller in radius. So how have I fucked this up? Pardon? We're taking what? Yeah, the join, after the join, yeah. So, you know, if we're using realistic numbers here, then we should be okay. What I'm going to do is go back into my cluster and just make sure that my, like the dimensions that I'm using for these sliders is just a bit smaller. So I'm going to set that to point as 3 so that our finger joints are sort of squished up a bit so that and the thing is you're going to need to finesse these things, okay? Does that make sense? So I'm just finessing these numbers so they work. So now I can make my cylinders a little bit bigger so that they're effectively going to trim all these edges. Okay, then we are going to take our joined curve, take our cylinders, and we're going to use this component called trim with B reps. The plural S is important here. We're going to place our curve our joined curve into the C, and our B reps, our cylinders into the B. I apologize. This is very overwhelming. Needs to change.
It's annoying because every time I open the
Cluster.
cluster to edit it, the multi-line data thing breaks and I have to make a new panel and I'm
Oh, really?
not doing it.
Just remove then in that case, remove anything that needs a multi-line panel.
It's just the one.
Right. But if you can remove it from the script, or you can also do this. Take your panel, plug it into a data component. So 6 and 5, 4, multi-line it, right? Then in the data component, right click and select internalize data. And then that'll store it in that instead of in the panel. Yeah, this is why I suggest using Windows, because they haven't ironed out all the problems with Rhino for Mac. Okay, so the output of this gives us all the curves that are inside the B-reps and outside. So we want the ones that are outside, like so. So that's trimmed them, right? And we can basically use the exact same process of connecting curves. So if we grab and copy and paste our connect curves component and plug our new trimmed curves into that, that'll create our closed triangle. Okay, the nightmare is almost over, okay? So, when we laser cut something